Hello everyone, continuing to our next chapter, Vertical Cavity Devices VXL. History of VXL. In 1978, Professor Kenichi Iga invented the vertical cavity surface emitting lasers. In 1979, the first report of the VXL itself. In the mid-1980s, VXL research has significantly increased the development of semiconductor distributor bright reflector (DBR) mirrors, and the advent of the Internet, low-cost laser sources which could be easily coupled to optical fiber were in great demand, which stimulated further research toward continuous improvement of VXL performance. In the mid-1990s, an industry was established by numerous companies manufacturing VXL, driven by the continued development of VXL applications. Since the year 2000, VXL production has grown to more than 50 million manufactured annually, and nearly a billion have been deployed around the world. Without a doubt, VXL can be considered the laser source for the information age. The advantages of VXL: it is excellent coupling to optical fiber, low operation power, low cost, which translates to high volume manufacturing capability, excellent lifetime characteristics. This is due to the monolithic epitaxial structure. The applications of VXL, for example, 650 nanometer, ultra-low cost plastic optical fiber systems for the use of potentially in automotive applications. For 850 nanometer wavelength, this is used for position sensing, for example, our mouse. 1300 and 1550 nanometer, it is used for optical communication, for example, access network card. More than 2000 nanometer, which is in the mid-infrared wavelength, this is used for gas sensing application. VXL structure. This is a typical VXL structure of gallium arsenide. It consists of three components. The first one is the optical medium, which the one who generates photon, for example, gallium arsenide, or any other semiconductor quantum wells. The second part is the excitation source. This is where the electrical current injected into a p-n junction. And the third part is the optical resonator, which is the optical cavity needed to build up the photon density required for stimulated emission. Gallium nitride-based VXLs. The first one is the distributed Bragg reflectors. In gallium arsenide-based VXLs, DBRs consist of alternating layers of gallium arsenide and aluminum gallium arsenide. This is to permit the electrical injection through the DBR and provide high reflectivity. Gallium arsenide, aluminum gallium arsenide DBRs is also well lattice matched to the gallium arsenide substrates. Conversely, three nitrides, these require no straightforward methods to form lattice matched, high reflectivity and conducting DBRs. So to overcome this challenge, overcoming the lattice mismatch led to variety device structures modifications, including the first one, hybrid structures with one epitaxial and one dielectric DBR. The second one is the double dielectric DBRs by substrate liftoff or thinning. For the first solution is the epitaxial and dielectric DBR. However, this process requires a long time. It requires around 20 hours per DBR and crack-free. This is high reflectance DBR with wide stop bands, which is a difficult structure to achieve in a device. As a solution, a periodic air gaps is realized to enhance the reflectivity of DBRs. The second solution is through the removal of the substrate. This is a double dielectric DBRs. However, this method of fabrication complicates the device fabrication, which translates to a significantly cost increase of this fabrication. However, The solution to this problem is by lapping or polishing technique on the freestanding gallium nitride. Band gap selective photoelectrochemical PEC etching also can be used for the substrate removal. Carrier transport across multiple quantum wells. GaN-based VCSELs, it has around 10 quantum wells to minimize the sensitivity to misalignment of the active region. Negative side of these multi-quantum wells MQW active regions translates to poor carrier transport. Non-uniform carrier distribution in MQW active regions was observed via simulation. Through this problem, there is a solution. The solution is the insertion of N++ GaN or P++ GaN tunnel junctions between the quantum wells, this including a single tunnel junction in the middle of a 10 quantum well active region. Uniformity of the carrier distribution can be greatly improved. The output power also is doubled. Lateral current spreading. GaN-based VCSELs, like conductive DBRs, requires to have intra-cavity contacts and lateral current spreading across an injection aperture. Uniform lateral spreading of current across the aperture important requirement for realizing a large overlap between the optical mode and the carrier profile. P-GaN is highly resistive, is around 2 ohm/cm. It is not a good candidate to spread current across the aperture. Hence, conducting oxide ITO has commonly been used as the current spreading layer. ITO has a high conductivity than P-GaN. Not an ideal solution, however, due to the current spreading remains an issue for larger device diameters higher than 10 micrometers. So, as a solution, the inclusion of novel 2D materials with high transparency, which has a high lateral conductivity within the cavity, might also provide opportunities to improve this current spreading problem. Graphene is the one of the possible current spreading layer for the GaN-based VCSEL. As you can see here, this is a spontaneous emission from an LED with a 12 micrometer diameter aperture graphene contact. So, as a result, the difference between the dimensions of 4 micron, 6, 8, 10 and 12 micron, the current significantly increased from 10 until nearly 20 ampere over cm squared. This is for the dual layer of P-GaN. VCSEL with DBR with a lambda cavity for an external cavity structure. Alternative to electrically pumped argon-based UVC lasers, we use DBR with lambda cavity. This external cavity structure, electron beam pumped (EB pumped), is an important demand for the DBR with an emission window at a working wavelength called lambda cavity. Alternate stack aluminum gallium nitride with a composition of 0.47, 0.53 aluminum nitride bilayers in situ grown by LPMOCVD, which translates to low pressure metal organic chemical vapor deposition. Through this method, the reflectivity was increased around 81.3% at the lambda cavity. The maximum reflectivity achieved was 89.8% at the wavelength of 282 nanometer. This also resulting in stop band with a full width at half maximum FWHM of 24.7 nanometer. These are the same images of DBRs with different cycles grown on aluminum nitride templates. The first one have 19.5 pairs, second one has 39.9 pairs, and final one is the 59.5 pairs. Transferable dielectric DBR membranes called TDBR. This realize the planar GaN microcavities based on transferable high-quality oxide-based DBR. Unlike what you've been shown before, The DBR is directly deposited on the surface of VCSEL. This, however, is not always feasible. TDBR membranes is versatile and is used as a top mirrors. It has a high reflectivity, nearly 97% near the UV region. These are the example for silicon pentoxide, tantalum pentoxide DBR on a gallium arsenide substrate. First, we spin coat the polymethylene culturamide PMGI layer on a gallium arsenide substrate. This PMGI layer is the layer for the liftoff process, and followed with the photolithography for the pattern intention. And then we evaporate the 4 pair of DBR on top of the pattern and also unpatterned layer, followed with the layer liftoff, and then left with 4 layers of silicon dioxide tantalum pentoxide DBRs on the gallium arsenide substrate. And then this layer can be removed and transferred onto another part of the device. Those fabricated 4 pairs of TDBR is then transferred here on top of this GaN-based membrane containing 38 GaN argon quantum well on top of 10 pairs of same DBR on silicon substrate. This results in a strong coupling region of a Rabi splitting of 68 MeV at room temperature. The shortest wavelength VCSEL, shortest wavelength ever reported in 2020 is 280 nanometer until 320 nanometer. This can broaden the application towards disinfection and medical treatment. This requires an electrochemical etching technique to remove the substrate and create smooth argon membranes. This figure shows a 2.5 lambda aluminum gallium nitride with a composition of 0.6 and 0.4 respectively. This cavity is including 3 aluminum gallium nitride quantum wells sandwiched between 2 hafnium oxide, silicon dioxide, HFO2, SiO2 DBRs. The top pair of DBR is a 10 pairs DBR, has a start band centered at 320 nanometer and measured peak reflectivity above 99%. The bottom reflector ends with an additional DBR pair and aluminum mirror. The reflectivity of the DBR is enhanced at the emission wavelength through this structure. Even more importantly, the reflectivity is also enhanced in the short wavelength side of this DBR stop band at 266 nanometer pump wavelength, which promotes recycling of the nano-absorbed pump beam photons. The bottom DBR is deposited on the grown epitaxial surface, whereas the top DBR is deposited after the flip chip bonding, and the N-polar aluminum gallium nitride surface exposed by electrochemical etching beforehand. The etched surface figure here has a root mean square of 1.7 nanometer on a 5 by 5 micrometer squared area, which is similar to the 2.2 nanometer as grown here shown, demonstrating a capability of the electrochemical etching to create a smooth etching. The smooth etching actually was achieved by using a multi-layered sacrificial layer, which promotes etching at the sacrificial layer and cavity interface as seen here. This enables the incorporation of layers with a aluminum content without degrading the crystal quality structure of the device layers, and the built-in polarization field yields sheets of high carrier concentrations, both of which enhance the selectivity and result in smoother surfaces. This figure shows the process flow and optical images for the fabrication process. So this is the before the processing. As you can see here, you have the substrate, sacrificial layer that is used for the etching later, and the active region and S-grown architectural structure. And B is the after MESA dry etching, followed with the C after evaporation of electrochemical etch contact here, and then the first deposition of DBR of HO4 and SiO2, and then DBR etching to remove this DBR for the contact exposure, and then aluminum deposition on top of the DBR, followed with the Ge silicon dioxide deposition here, and followed with another metal deposition in H of titanium and gold. And I is the photoresist to protect this layer for the following electrochemical etching. And then J, as you can see here, the sacrificial layer is gone. So this etching actually was done by using a 2 electrode setup using 0.3 molar nitric acid as an electrolyte. A constant positive potential of 30 volts was applied to the sample relative to the graphite counter electrode, leading to then an anodic etching. The etching was done at room temperature with no intentional illumination, and the electrolyte was stirred using a magnetic stirrer bar. The progress of etching was monitored in situ using stereo microscoping, and the etching of the mesas was completed for around 35 minutes. As a result, you can see here the sacrificial layer was gone. And K is the photoresist removal, and then followed with L, the thermocompression bonding of AU, TI, and SI, and then M after the thermocompression bonding, and N, 10 pass of the second part of the DBR was deposition, forming the final UV. And this shows the top view of optical image of the fabricated UVB VCSEL after the final processing step. These are the TEM images of overview as a grown VCSEL structure with the bottom cavity layer, the first barrier, active region, last barrier, and the top cavity layer. This top cavity layer shows a deviation only around 2% from the intended structure. These are the zoom high resolution image of TEM, and you can see here the structure and the thickness of the active region itself. The quality of the QWs is very sharp and very high, with sharp interfaces between the QWs and the barriers. Literally here you can see a different color, and this is a very homogeneous growth of the device. And so this is the figure of the emission that showed a single mode lasing. The single mode lasing peak at 307 nanometer with a resolution limited line with a degree of 97%. Thank you everyone, and have a good day.